Ivana, he's here right now with us. She's doing a PhD in quantum physics at the Max Planck Institute of Optics, and she will be talking with us today about the future. Is the future quantum? Ivana, hi.
Hi, glad to be here.
So sorry, Ivana. Please let us know what is happening in the future.
Thank you so much. All right, I hope that everybody can hear me and see me properly because I am connecting from Zoom at my own home, isolating. Now, I am a scientist of a bit of a different type than the rest you've seen today. I don't deal with living things. I'm a theoretical physicist, which means that I mostly do things that closely resemble mathematics. Now, I know, sounds terrifying, but I got into physics by being so interested in big, cool things like astronomy when I was in high school. That slowly transitioned to me learning about more interesting, more intricate, and less simple things in physics. So what I'm here to talk to you about today is the topic I'm working on for my PhD, quantum physics, in particular quantum computing. Now, when people hear quantum, they often aren't really sure what that means. If you've learned in high school about the light experiment where we can think of light as both a wave and a particle, that might ring quantum to you. But some people like to interpret this as saying, well, if everything is both a particle and a wave, doesn't that mean you can also be a wave? And maybe if you run really fast and you're very lucky, you can just run through the wall, just like waves and the sea can crash through the rocks. It, of course, isn't that simple or that easy. It's really hard to explain exactly what we mean when we talk about quantum physics without using lots of math, but I'll try. So what makes quantum special and different? If you think about classical things, what we mean by that is, for example, with computing, think about your computer. It works based on zeros and ones. I'm sure you've heard of that somewhere. It's a channel for electrons. It's either open or closed. It's either up or down, like this pencil. I don't know if you can, there we go, up or down. And if you want to create a big system of classical particles, what you do is you get a lot of these classical things. You can flip some of them down, some of them up, change things around, and that's how you create codes that tell machines what to do. So you can use physics to create beautiful, intricate, logical sequences that power things such as the computer or phone you're using to watch the stream right now. But for quantum things, it's not that simple. It's not just up and down. We have a plethora of different ways we can think about quantum stuff. So if in classical physics we have a bit that's either up or down, in quantum we have a qubit. And you'll notice that a lot of quantum things just attach a Q at the beginning of the word, so it's not a bit, it's a qubit. And we have so many different ways we can turn it and so many different states it can be in. And when you take lots of these, it can become really complicated. The amount of things that you can do with them becomes more interesting than just having up and down. And the more of them you add, the more complicated it gets. Now, this allows us to think about quantum computing and quantum physics as something that lets us explore a completely new dimension in physics and in computing. Of course, the things we want to achieve are kind of bordering on magic. The nature that we live in is it's actually quantum. It's not classical. And if we're able to create quantum computers, we can mimic this nature and try to model things that exist. So for example, if some of these beautiful life scientists that we're talking to you today want to create vaccines or medicine, or perhaps some agricultural additions to help crops grow better, they can use, hypothetically, a quantum computer to help them predict whether their work in the lab actually makes sense, whether there's any point in trying something. But that's only the start of it. Because it is so complex and so different than what we've been using so far. So many different things can be done. One of my favorites is in cryptography. Now, cryptography is the science of trying to send a message from point A to point B and make sure that it's completely secure. So you, for example, take a message here and you translate it to gibberish, but you know which letter corresponds to which other letter. Your friend knows the code as well, and when they receive the gibberish, they can decode it. Now, if you take quantum physics, because it is so different than classical, we call this property entanglement. If one of these quantum bits, qubits, is in a particular state and we measure it, we see it in that state. If it is entangled with another one, regardless of where it is, we will affect the way we see this one and the other way around. So we can create some beautiful complex structures in computing and science. But it's, of course, not that easy, because even if you see me juggling like this, these are just 3 balls. How many bits do you think are in your computer right now? How many bits do you think we need to make a really cool classical quantum computer to create vaccines? Well, more than this. And the more balls you have, the more focus you need to have before one of them just drops. Now, when people ask me what will a quantum computer look like, this is the reason why the only thing I can show them is a box. Just a closed box, because if we were to open this quantum computer and let the light in, or if, God forbid, somebody walked into the room and made noise or stepped on the floor too harshly to vibrate everything, it would decohere or destroy the state that the computer is in. So it takes a lot of focus and a lot of things, like, for example, the temperature of a quantum computer. To make sure that everything stays the way it's supposed to be, we have to be very careful with it. The temperature has to be lower than that of outer space. So when we think about quantum physics and quantum computers, there are so many options we can go in. And of course, you need to know a lot of mathematics to get there. But what I want you to understand about this is that it's unclear whether it will be easy or hard to do this. There are different ways quantum physics can be molded and used to create beautiful new technology. So many different researchers across the world are using different ways to try to achieve a quantum computer, but not all will work. We don't know which ones will work. This is a completely new field of science, and we're trying our best to figure out the best way and the safest way to make sure these little closed boxes work, and that 5, 10, 15, or maybe 50 years from now, all of us will be able to use quantum computers in daily life. Thanks.
Quantum does sound very futuristic and science fiction. Not sure how I would be able to deal with a quantum computer. Apparently, I cannot even deal with a normal computer. However, we do have some questions that I would like to ask you from our audience. What are the practical applications of quantum computers? This is a question from Facebook.
Right, so there are so many, honestly. The way we look at it right now is we're trying to create either things that are very easy or things that will show us that there are options that we can reach. So these two things that are sort of easy would be these models of nature. So for example, quantum chemists are people who might be using a quantum system, quantum computer, which is just a system of qubits, to model a particular, let's say, medication, molecule, compound, and to see whether it does anything cool. So these are the simple things that we can do. And you might also hear these complicated things. They're called proofs of concept that people do. You might have heard last year, Google did some really interesting experiments with their quantum computer. They were actually useless. They didn't do that much. So one of the things that we try doing is try to prove that quantum computers really can do these things that mathematicians, such as myself and theoretical physicists, actually have a point. That if we manage to make these things in real life, they will be able to do cool things. So there are so many things that we still don't know, and the only way we can go ahead is try to find a middle line between theory and experiment and what we can accomplish with the theory that we have.
Within that line of thought, on YouTube, Judy actually asks a question: if we can make actual experiments, or if it's all maths.
Oh no, it's definitely experiments. So one of the really cool things that you can do, there are actually, I talked about cryptography for a little bit, and there are really cool things happening in cryptography right now. There are research groups across the world that will send a little satellite up to space and have it have a laser link, like a laser pointer. It just has to shine a light to Earth, so they have a connection, and using this laser they can send information, quantum information, to each other. So if you, on Earth, have a message you want to send to the satellite, or send to the satellite to send to your friend in the other part of Earth, you can encrypt it using quantum physics. So a really, really, really interesting thing about this is when you have these messages, you send it from here to here. If anybody reads the message on the way, this entanglement we were talking about collapses. And what you get at the other end is different than what you would expect. It's actual gibberish. It doesn't work. Just like somebody jumbled up your message along the way. So you can definitely tell if somebody's been reading your messages, and you can keep all your information, which I guess is becoming increasingly important in the internet age, especially since we've been working from home and studying from home these days. You can keep everything perfectly secure.
We have some other question also from YouTube, from Samantha. What are the conditions where one needs quantum physics to describe a system instead of the classical ones that we are all used to?
This is a controversial opinion, but if you were asking a physicist, what they would tell you probably would be always. Because nature is quantum, it's not classical. So when you learn about the laws of motion, the Newton stuff in school, it's just kind of like it's not very precise. It's just what we can see in very simple terms. When it becomes important to think about these quantum effects is when we're dealing with things that are either very small or very cold. If they're very cold, then there's not that much heat energy happen, like exchange isn't happening, and quantum effects have a higher meaning. So, but also in situations when you have a lot of energy, it turns out that classical physics is just an estimate, an approximation that is easier for us to understand, where the world is actually quantum. We hope there might be something else we discover in the future.
There's actually a very interesting question from Mart in YouTube. How many qubits do you need to encrypt a 200-word message?
You're kidding.
No?
Okay, so a 200-word, well, it would depend on how many letters each word has. But if you imagine a classical encryption, you could, for example, say that each letter has a different sign, right? So if you say my A is actually going to be my B, my B is going to be C, and so on, that's one way of encrypting. But there are other ways. For example, you can say that for my first word, I'm going to use A as B, B as C, and so on. And for my second word, I'm going to use A as C, B as D, and so on. There's so many different ways that we have, throughout history, for thousands and thousands of years, encrypted things. So also when you talk about quantum encryption, there are so many different things that we can do. It's a difficult answer to give, but it would definitely increase in size as you increase the amount of information. So if one letter is one piece of information, you would need at least one bad boy qubit for it, and so on.
So it's not about so much as the 200 words, but how much you want to put into each one.
Exactly. So there are some cryptographic methods. For example, if you know about the military cryptography, where sometimes they will, instead of one word, for example, they won't say east. They will say on the road. They won't say west. They will say on the beach. So there are different ways of cryptography, but you would definitely, as you increase the amount of information, have to increase qubits, and it would not be, most likely would not be smaller than 200.
Also, because you were saying in your talk that in the future all of us could have a quantum computer, which I'm not very excited about. It is true that quantum computers need a lot of energy to run. How would this impact climate change if all of us have a quantum computer?
Oh, that's an easy one to answer. You might know about these stories back in the day when classical computers were still very new, and there were people saying, who's going to need a classical computer at home? Maybe 5 for the whole world. This is too expensive, too difficult to manage. This is literally what we've been saying about quantum computers of the future. So imagine the satellite that we sent into space. It doesn't just have to have a laser to take information. It can actually, hypothetically, have a quantum computer. And as long as you can send a laser to it to send it information, and it can send you information back using this laser, we can put it in space. And if it's in space, well, it doesn't really affect global warming. So this is sort of what we're expecting, at least the beginning stages, to look like. Of course, right now, the most complex quantum computers are on Earth, for sure. But if one day we want people to have access to them, we will probably shoot them into orbit so that they're more accessible to everyone. And of course, when they're in the deep, dark cold of space, their heat doesn't matter that much.
That's a very interesting idea, putting computers in space to help us on Earth. Another very interesting question, which is actually very true for many sciences, is that scientists always talk about the positive of their research, but what are the unsafe or the negative sides of quantum computing?
Yeah, this is really hard to phrase in a very short amount of time. If you want to chat about this with me, there will be a Twitter handle in the chat at some point, and I would be happy to do that. Some of the basic, we've been talking a lot about cryptography. One of the things about cryptography, quantum cryptography, that is kind of dangerous, is that you would not be able to know what happened if the information is encrypted. So let's say somebody breaks the law and talks to their friend about it using quantum encrypted information, you wouldn't know. But what's more important for us right now is there are these algorithms in quantum computing that have the possibility to search through databases really, really quickly. And cryptography right now, as we use it, you might want to look up something called the RSA algorithm, just the letters RSA. This is the cryptographic algorithm most of us use all the time online and so on. And if you had a quantum computer, you could break that really quickly, because the goal is just to find a number or numbers that divide a particular really large number. So right now, classical cryptography is based on us doing something that's easy in one direction to encrypt and to make sure that it's difficult to do in the other direction so that potential hackers can't get to it. But if a hacker had a quantum computer, it would probably take them 2 minutes to get the password to your email account. So that's something we need to think about in the near future.
Okay, thank you so much, Ivana. Unfortunately, we have no more time for your questions. But as Ivana just said, don't worry. We will leave her Twitter handle down below in the chat, and you can ask her, and also her website, and you can ask her as many questions as you wish. Thank you so much, Ivana, for coming. And
thank you for having me.
Bye.